Our next talk, I believe, is going to be given by Ben Turner of Dan Brown and Associates on a topic that I've come across here in the Puget Sound when driving these kinds of piles into the very dense glacially overridden soil. So I'm looking very much forward to seeing what Ben has to share. Welcome, Ben.
All right. Thanks, everyone. I think we'll see the slide here in a moment. This presentation is regarding a project that I worked on with Dan, who I see here in the audience. And it's really a forensic study of the hollow concrete cylinder piles pictured here on the Hathaway Bridge in Panama City, Florida. And as the name suggests, we were trying to determine what caused the longitudinal cracking in the cylinder piles. It's interesting to hear from Armin that he's experienced that here. It turns out to be a pretty well-documented problem, and yet, as an industry, we don't seem to address it very well yet. So hopefully we can shine some light on it here today. I'll just go through briefly historically to mention that hollow concrete cylinder piles are used on a number of well-known structures, including pictured here the 23-mile-long Chesapeake Bay Bridge Tunnel, built in the early 1960s. You see in that smaller photo at the casting yard where they have the pre-stressing strands exposed before or during stressing, and then they'd cut off the free ends, obviously. Also, the Coronado Bay Bridge, going from San Diego to Coronado, is supported on hollow concrete cylinder piles. You don't see them here. They're below the pile caps. Built in the late 1960s. So why would you do this to begin with? Well, if you consider a solid pile cross-section that would have a diameter of, say, 40 inches, maybe it's a drilled shaft, maybe it's a large pre-stressed concrete pile that's solid, and we take that same amount of concrete and we push it out to a hollow shape, so in this case a 5-foot diameter with a 7.5-inch thick wall thickness, that's the same amount of concrete, but the moment of inertia has increased 4 times. And so it's much stiffer laterally, which is what makes it appealing for applications where you have a long unsupported length, like a bridge through water, or if there's a significant distance till we get down to something stiff below the mud line. To give a little bit of a local perspective, there are a number of structures here locally, bridges supported on hollow concrete cylinder piles, including 22, at least that statistic I think is about 10 years old now, but according to the Washington State Bridge Retrofit Program, just on the major freeways that service, or interstate highways that service the Seattle area here. One of those picture we just heard about, I didn't realize it was going to dovetail well with that, but the reason you just heard Jeremy explaining why the SR 520 bridge had to be replaced is exactly this. It's on these hollow concrete cylinder piles, and it turns out, we know now, they're very poorly suited for high seismicity regions. The reason for that is that, like other concrete elements, we get spalling under large deformations or cyclic loading, but because this is hollow in the center, not only are we getting spalling on the outside, but also on the inside. And so with our starting off with a fairly thin wall thickness, when we're losing concrete on the inside and outside, these things completely deteriorate pretty quickly. They have no axial load carrying capability or lateral load carrying capability. In fact, WSDOT was behind a series of tests done at UCSD on hollow cylinder piles, which included even an attempt to retrofit them by wrapping them with FRP. And as you see highlighted here, the performance was not desirable. The failure mode was described as an instantaneous implosion, which I don't think anyone would be comfortable with as a designer. And they also went on to say that there's really no effective way to retrofit these. So structures in high seismic regions that happen to be on these are pretty much slated to be replaced with a different foundation type like we just heard on SR 520. The subject project here is the Hathaway Bridge in Panama City, Florida. Construction was finished in 2003. Most of the piles were driven in 2002. And actually that detail I showed on the previous screen as the example is the detail from this project. So they're 5-foot diameter with a 7.5-inch thick wall between the inner and outer diameters. A couple years after construction, underwater surveys by a diver revealed that about 20 of the piles had longitudinal cracks. So longitudinal meaning vertical and the longitudinal axis of the pile. And they extended from the mud line upwards between 5 and 25 feet. Presumably, they extended below the mud line also, although they did not attempt to excavate below to see how deep the cracks went. At least that's my understanding. So what's pictured there kind of looks like a starfish is the gloved hand of the diver. So you see from his finger, his or her finger, that crack is probably on the order of a 1/4 inch to maybe 3/8 of an inch thick. It's certainly not a hairline crack, is what I'm trying to point out. And it's probably large enough that the spiral reinforcing steel that is inside this pile, if not ruptured, then at least underwent, it yielded and underwent significant plastic deformation. That's the only way a crack this wide could have opened up. So our task was to try and figure out what happened here. Why did these cracks occur? Why didn't they occur on the other couple hundred piles? They only occurred on about 10% of them. So we started with the easy stuff. We tried to identify, well, were the ones that cracked the longest or perhaps had the highest flow counts for the driving criteria? Maybe that's the easy explanation. Well, nothing's ever that easy. It turned out they were at the upper end of the ranges of length and flow counts for the driving criteria, but they were not the extreme. They weren't the longest. They weren't the ones we hit the hardest necessarily. It was interesting to note that about, 3/4 of them exactly were clustered at one pile cap near the center of the bridge, or 2 pile caps for the 2 separate bridge structures, but at essentially the same location on the 2 adjacent bridges. Diving into the literature on this subject, we found that it's been documented for 50 years that these cylinder piles are commonly found to exhibit this type of longitudinal cracking. In fact, that second report by Avent and Mukai in 1998 points out that the 2 structures that I highlighted with photos at the beginning both have longitudinal cracks in the cylinder piles that have been discovered since then, and so do a number of other examples of cylinder piles as documented by these other reports. The 2007 paper by Rausch and Webster and then the 2008 paper by Malhotra go through or postulate a number of potential mechanisms that could lead to this. So 3 of those, and there are a lot more that they point out, but I think the 3 most convincing ones are listed here. Then we'll go into a little more detail, particularly on this first one, the Poisson effect due to uniaxial compression, which I'll define graphically here in a moment. Internal pressure, so because this is a hollow cylinder and we're driving it, there's a combination of air and or water in most applications inside. So there's a dynamic compression of that fluid inside, which then puts a pressure on the wall and wants to push out, which could potentially be enough to cause rupture or splitting. That's combined with the fact that a soil plug may or may not be forming. So this thing is sort of getting compressed from the top and or the bottom simultaneously as it moves down. So there's a degree of complexity there, certainly, with that aspect of the behavior, the hydrodynamic pressure inside. This last one is kind of a catch-all, actually, for a number of mechanisms. The fact that you're driving this pile and it's a dynamic situation, it means that everything about it is complex in terms of the mechanics. One aspect of that is that as the compressive stress wave travels down the pile shortens slightly because it's in compression. And if you take a pre-stressing strand that's locked off under tension and you shorten it a little bit, it's effectively relaxing. So the load drops off. So that further changes the stress distribution, at least locally, in the pile as that stress wave is traveling down. Okay, so looking at the Poisson effect, this applies to all engineering materials, at least most of them that we deal with, which is that when you put an axial compressive force onto a material, it wants to expand in the other orthogonal directions. So here that would mean when we're putting an axial compressive force down the pile from the pile driving or from the pre-stressing force, it has a tendency to want to expand in the radial and hoop directions, okay, as defined graphically here. If you think about what would cause a vertical crack to form, it's tension in the hoop direction. We have to have this thing pulling apart in order for a crack with that orientation to open up. And I'll point out that this is not unique to cylinder piles. In fact, there's an ASTM test designed to directly measure what's called the splitting tensile strength of concrete. And you do that by taking a concrete cylinder and loading it in compression until it splits, just like this. So we certainly can't pretend that this type of behavior is not a known mechanism. In fact, we take advantage of it and do it on purpose for that reason. So we're going to put some numbers to this mechanism and see if it could possibly explain what happened. This is high-strength concrete because it's a precast pile. The design strength was 7 KSI. So referencing this ACI report on properties for high-strength concrete, we estimated the tensile strength and modulus to be about 620 psi and 4,500 ksi respectively. We can relate stress, strain, and modulus using Hooke's law, and we would estimate that it would take a strain of about 0.014% to cause a tensile splitting failure. And that's confirmed with values reported in that same ACI report that on average, high-strength concrete will rupture in tension when experiencing a strain of about 0.014%. Okay, kind of looking at the other side of the coin, what would you be interested in if you were a designer on this project? And it's knowing that it's pile driving of a concrete pile. Well, you're going to look at the maximum compressive driving stresses that are allowed, in this case by the Florida DOT 455 spec, and you're interested in maximum compression and tension as the wave travels up and down the pile to avoid failure. Sort of the normal failure mechanisms that we're looking to avoid or damage mechanisms during pile driving. So that's a function of the compressive strength of the concrete and then also the effective pre-stressing force. It comes out to just over 4 KSI for the properties of the piles on this job using the design compressive strength. The measured driving stresses during installation were below that, ranged between 3.5 to 4 KSI. So per the spec, these piles were fine. And you would be led to believe, if you believe that the spec is reality, that there shouldn't be any damage, especially since the actual concrete strength was 8.5 KSI on average, so higher than the nominal compressive strength. Okay, now we're going to go through a short exercise to relate that to hoop strain. So the maximum compressive stress during driving of about 4 KSI is additive with the pre-stressing force because the pre-stressing is trying to compress the whole pile. So we can calculate strain in the axial direction using the measured dynamic modulus. And then we can calculate a hoop strain from that axial strain just using the simple Poisson's ratio or relationship. So for concrete, the Poisson's ratio is about 0.2, and we would calculate there a tensile strain in the hoop direction of about 0.017%, which you'll recall exceeds the value at which we would estimate that cracking would occur of 0.014%. So that is significant because that says that even when we take into account the as-built strength is higher than what it said on paper, and knowing that the driving stresses were below the allowable compressive stresses per the FDOT spec, mathematically we compute that the tensile strain is enough to cause cracking because the strain in the hoop direction would cause cracking of these piles. So again, I'll repeat, you're installing this in accordance with the spec, and yet we're basically calculating that it should be cracking. So this is undesirable. We all know that in reinforced concrete, we design the concrete to take compression, and then we add steel to carry the tension. So hollow cylinder piles are no exception. They usually have a spiral transverse reinforcement detail like shown here. This is a standard plan pile per the FDOT spec, just used straight out of their spec book for this project, the 5-foot diameter pile. At the top, where you have stress concentrations from driving, they have a tighter spacing on the spiral. So it's a 3/8 inch diameter spiral, and it's for 10 feet, they're at a 2-inch pitch, and then in the center of the pile, it's at a 4-inch pitch. So there was no longitudinal cracking observed at the top, whereas in the middle at the lower pitch, that's where the cracks were observed. So the transverse reinforcement seems to come into play here, as you would expect, because we provide reinforcement, again, to have strength and tension. There's an often cited report from the Portland Cement Institute from 1993 about pre-stressed concrete piles, including hollow cylinder piles, which has commentary directly on this issue. It actually says that the spiral reinforcement should be designed to carry the splitting tensile strength of the concrete. So in other words, the tributary area that corresponds to one spiral, the spiral ought to be able to carry the force that the concrete has when it ruptures in tension, so that if that occurs, the load is immediately transferred to the spiral reinforcement. And as a rule of thumb, they point out that that usually takes between about 0.6 and 1% as a spiral reinforcement ratio, which is defined like this for a hollow cylinder pile: 2 times the area of an individual spiral bar divided by the product of the wall thickness, the outer versus inner diameter, and then the pitch. So for the piles in the middle section here on this project, that ratio is about 0.4%. So it is below what they recommend as a rule of thumb, providing at a minimum to resist cracking, which of course occurred. We also performed a dynamic analysis of the problem, not necessarily to, quote, see what the answer was, but just to get further insight into, did the dynamics of this come into play significantly? That is, when we consider inertia and damping and the velocity of the wave traveling down the pile as computed from a GRL weep analysis, do we expect a vastly different relationship between the magnitude of the compressive stress and then that tensile strain in the hoop direction that we're interested in quantifying? And the answer was no. We did not see a significant difference, which confirmed our feeling that doing this in a simplified manner, basically a static, the simple static calculations I did, is sufficient. The other mechanism that I alluded to is hydrodynamic pressure inside the cylinder. So as the cushion of air, the volume of that air decreases as you get closer and closer to the surface of the water, like you see the one here that's actually underwater, goes down, the water pressure goes up exponentially. And if you're driving these things with zero air cushion, you would compute mathematically, at least based on the velocity of the hammer, a hydrodynamic pressure on the order of 500 psi. And you can relate that to the stress in the hoop direction directly with the fairly simple equation shown there. And we came up with 1650 psi. So that's well in excess of the splitting tensile strength of the concrete of about 700 psi. In other words, if you drove one of these things, if you struck it with the hammer at the full velocity with truly zero air cushion, that would definitely be enough to rupture it. Now, it's unlikely that that condition actually applied on any of these piles, even though some of them are shown here in the final condition, totally underwater. That's affected by the tides at the time of driving, although I do believe that the inset picture is one of the groups which had several of the piles damaged. So it does seem to be a factor. Also, the cushion is pictured here. That one's in pretty good shape, but as you know, the cushions wear out, and so that influences the relative stresses that an individual pile experiences depending on the condition of the cushion when they started and ended driving. So why did some of them crack, but not all of them, was sort of the other aspect of this we were looking at. And we postulated a number of possible explanations. One, variation in material strength. Even though we know on average the strength of the concrete, for example, was higher than the design specified strength, likely the yield stress and ultimate strength of the steel were as well. There's going to be variability across the site that we don't really have sufficient records to assess. So of the concrete and of the reinforcement. We do know there's variability in the ground conditions across the site, although we weren't able to pinpoint anything specific about the location where the damaged piles seem to be clustered in terms of the ground conditions being different there than at the other groups. Although that may have just been, frankly, from a lack of adequate data to be able to characterize the subsurface on that refined of a level. The condition of the cushion, of course, is influencing the maximum stresses experienced by an individual pile and how many blows an individual pile is subjected to at the maximum blow count. And of course, where it sits relative to water. Another thing that's interesting to ponder is that these precast piles have a seam from the way they're constructed in the casting yard, and there's likely a stress concentration at the top at least because of a slight eccentricity when you're driving the piles. Everything's never going to be perfectly aligned. So maybe it's kind of a worst case scenario where that seam aligns with the maximum stress due to some eccentricity, and those are the piles that cracked, and in other cases, things were in a more favorable orientation to avoid cracking. So all these factors potentially explain why cracking did not occur everywhere. So to wrap up here, the pretty obvious lesson, I think, is that we need to take a look directly at what's going on in the hoop direction in terms of stress and strain. Doing so is almost trivial in terms of the calculations, but nonetheless, that's not directly accounted for in the standard specs or in a document like AASHTO. The maximum compressive stresses that just look at limiting, or avoiding crushing or tensile failure in sort of the classic sense of driving concrete piles may be too high because it doesn't take into account this directly. So you could come up with a modified maximum allowable compressive stress during driving that makes sure you stay below the tensile strain limit of the concrete. we should also be providing enough transverse reinforcement to handle these loads as was recommended in the PCI report. I think that's pretty straightforward. And avoid driving these things completely underwater. They're often vented if they're going to be driven close to the water, and that's certainly recommended. But I would completely avoid driving them when they're full of water because the water hammer effect could definitely lead to a failure. So that's it. I think I just want to say that this points out a good lesson for all of us, which is that we rely on the code, you know, as a guiding document, but that doesn't guarantee that it always captures all possible scenarios and everything. We still have to think on our feet as engineers and be on the lookout for things like this and ways to explain it and design around it. So, thank you.
I don't think we've got